In this lesson, we're going to talk about simplifying radical expressions. So in algebra, we do simplifying a lot. And all that simplifying means is if we have an expression like x plus x, we like to write that in a different form that is equivalent, like 3x. So x plus x, that represents a quantity, but it's a whole lot simpler to write 3x. So simplifying just means writing things in different ways, but with the same value. Okay, so let's think about this. Let's say we want to multiply the square root of 25 times the square root of 4. Well, we could do that two ways. Maybe we want to square root first. Square root of 25 is 5. The square root of 4 is 2. And 5 times 2 is 10. Okay, that's one way we could go. Can you think of another way we might do this? What if we have the square root of 25 times the square root of 4? Well, maybe you might want to multiply those first. Let's just try it. Square root of 25 times 4 is 100. So that's the square root of 100. Well, what's the square root of 100? Remember, square root means what number squared equals 100? And the answer is 10. So we get the same answer. So the moral of the story is this. If we have two square roots that are being multiplied, we can either square root them first and then multiply, or we could put them together under one square root, meaning just multiply the two numbers, and we get the same answer. And this is always true. This is what we call a radical product rule. And it's not just for square roots. It can actually be for any index. So if we have the nth root of a times the nth root of b, well, that's the same as the nth root of a times b. In other words, we can take these two numbers, a and b, and we can multiply them so that we end up with one square root and the two numbers multiplied underneath. Okay? So, let's see how that works. So we got the square root of 2 times the square root of 5. Well, that's just going to be worth the square root of 2 times 5. We can put them under one square root, and that is the square root of 10. So that is simplified right there, okay? All right. So we've got, how about this? What if we got, binomials? Well, we've got x plus 5 and x minus 5. Those really need to be in parentheses if we're going to do this right. So we've got x plus 5 times x minus 5. Okay, now we haven't seen binomials yet in this course, or in this chapter at least. So how do we multiply those? Well, you remember we need to distribute. This is being multiplied here. So we've got to distribute the x times the x and the x times the negative 5. Does that look familiar? Hopefully from previously algebra experience there. We got x times x squared. We've got x times 5. That's going to be, actually it's a negative 5. So negative 5x. Now we got to take this 5 here and multiply it times that x. That gives us a positive 5x. And then we've got this positive 5 times this negative 5. And that's going to be negative 25. 5 times 5 is 25, but we got a positive times a negative. And we can simplify that a little further. We've got negative 5 times a positive 5, and that is, or negative 5 plus, negative 5x plus 5x, that is 0. Those cancel. Okay, those are gone. And so we have x squared minus 25. Now be careful. You cannot go any further. Are you tempted to square root this and square root this? All right. We're all tempted like that, all right? But don't do it because of this minus. Because if this is add or subtract, you can't just square root that and square root that. We have to leave that alone, okay? Well, how about this? Cube root. Oh, okay. Well, it also works for cube roots here. And we have 2 times negative 4. And we know what 2 times negative 4 is. That is negative 8. All right, and so we have cube. Oh, can we take the cube root of a negative number? We sure can. It's negative 2. Because remember, we can cube root negative numbers, but you can't square root negative numbers. All right. So again, we can put them together, and then if we can simplify them, go for it. Ooh, how about a fifth root? All right. So we have a fifth root, and we're going to multiply those under one radical. Now, this step that I'm writing here, we could probably skip in just a moment. All right, but that's really what's going on. Okay, but you could probably skip what I just wrote there and go right to this. Well, let's multiply. Now, careful, we're multiplying 3 times 2. 3 times 2 is 6. Now, what else are we multiplying? That's an x to the first, right? A little invisible 1 right here. What is x to the first times x to the fourth? Talked a little bit about that in the last lesson. X to the 1 times x to the fourth. We have a power rule. We're going to add those exponents, right? That's x to the fifth. And if it helps, write that out. That's x times, and we have this x times x times x times x. We have 1x times 4 x's, or all multiplied, that's x to the fifth. Okay, enough of that. So we got 6x to the fifth. Add those exponents. Ooh, can we simplify this any further now? Well, we don't know what the fifth root of 6 is, but we do know what the fifth root of x to the fifth. So here's something that we're going to be working on a whole lot. Okay, we can break this up into 2 square roots. We have the square root of 6 and the square root of x to the fifth. Now notice, what did I just do there? Okay, I just used this rule backwards. I took 1 square root and I broke it into 2 square roots. Why would I want to do that? Well, because I can deal with this, but I can't deal with this. I don't know what the fifth root of 6 is. You can use your calculator and find it. It's a decimal number, but I don't know what it is. But remember that these are inverse operations. The fifth root of x to the fifth, those are opposites. Okay, they cancel each other out, and that just leaves x, if you want x to the first, or just x. Okay, so x times the fifth root of 6 is the most simplified version. Okay, so that's the radical product rule. Next, we'll see how we can use that to simplify square roots. That last example kind of leads us to thinking, okay, how can we use this to simplify radicals with numbers? So if we have an nth root radical is simplified if the radicand, which is the number underneath, has no factors that are perfect nth powers. Now, there's a couple methods, all right? Now, if you go YouTube in it, you'll see all different methods, all right? And in some example videos, even in this course, you'll see different methods, especially if they're videos by other people, all right? But let me show you the simplest method for numbers like the square root of 18 is this. First thing we want to do is we want to factor the radicand to include one perfect power. In other words, this is a square root. So n is 2. It's a square root. So we want to take this square root of 18 and we want to break it up. Well, we want to say, all right, we want to say, what are the perfect squares? Remember the perfect squares? Perfect squares are 1. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. So on and so forth. Those are the perfect squares. And we ask ourselves, these are all numbers, first of all, that can be square rooted. I know the square root of 16, it's 4. I know the square root of 25, it's 5. Do any of these multiply into this? Are they factors of 18? Can you multiply 4 into 18? No, 4 times 4 is 16, but not 18. Can you multiply 9 by something to get 18? Yes, you can. It is 2. All right, so we can break up the 18 into 2 numbers. One is a perfect square, and the other is not. So we choose 9 times 2. This is a true statement, 9 times 2. Now we're using this rule. Let's look back at this rule. This rule here says I got a square root now with 2 things multiplied, and so we can go backwards. Whoops. We've been going forwards, but now we're going to go backwards, and we're going to break that up into 2 square roots. So that's our second step. Okay, we're going to use the product rule, the radical product rule, to take the nth power of each factor. Okay, meaning this, we're going to break it into 2 square roots. That's what the radical product rule says. We can pull that apart or put it together. Now, do you know the square root of 9? Yes, you do. I hope you do. I do. It's 3, because 3 times 3 is 9, right? Do you know the square root of 2? Oh, man, that's a weird decimal. If you plug in your calculator, it'll be like 1.414, and it goes on forever. So we don't know exactly what it is, so we're going to leave it as the square root of 2. So we have 3 times the square root of 2. We can simplify part of it, but not the other part. We leave it alone. Okay? Now, we don't usually write this little times in there, and so I'm going to erase that little times here. And so we'll write it like this, and we read this as 3 square root of 2. What it means is 3 times the square root of 2. All right, that's one method. Another method goes like this. And this is similar to what you might see on some other videos, but this first method is so quick and easy, you want to get used to that, especially for small numbers. When you have big numbers, then you might find it useful to do this. So if we have the square root of 18, first thing we want to do is do the prime factorization. What is that? Well, the prime factorization means we're going to take 18 and break it down into as small numbers as we can. 18, for example, is, let's say, 3 times 6, or you could start with 2 times 9. Doesn't matter. Okay, and 3 is a prime number, so I'll circle that. 6 can be broken down into 2 times 3. Those are prime numbers, meaning prime numbers means we can't break them down. We could break this into 1 times 2, but that doesn't help us. All right, we don't want ones. So the square root of 18 is can be written as the square root of 2 times 3 times 3. Or better yet, it's 2 times 3 squared. All right, so now we have 2 times 3 squared. We can break that up into 2 square roots, square root of 3 squared and the square root of 2. Now, the reason why that helps us is, see right here, see how it's written as a power, kind of like we did with exponents in the last lesson? Okay, so first thing we did was we broke it up, and we wrote it in prime factorization. Now we're going to break into 2 radicals, one that can be simplified. And we simplify the one, and we leave the leftovers under the other radical. So we're going to have this idea of 3 squared is 3, and the square root of 2 is kind of leftovers. We leave it alone, okay? Because the squared and the square root cancel each other out is kind of what happened there. All right, so that's one way. That works good for big numbers, because if you have a whole bunch of factors under here, everything that can be squared is going to come out. Everything that is not a square, that will be left alone. All right. So let's look at a couple examples and see how we can use this. And we're going to use this method 1 mostly, because we'll have smaller numbers most of the time. So let's simplify some square roots using that method 1. So the first thing we're going to do is we're going to break it up. We're going to look for a perfect square that goes into this. Now remember, our perfect squares are 1, 4, 9, 16, 25, 36. So on and so forth. Now, we don't care much about 1. We're going to start with these ones. Do any of these multiply into 50? Well, one of them does, right? 25 does. So we can break this into 25 times 2. And the radical product rule says we can go ahead and break that into 2 square roots. Do we know the square root of 25? We sure do. That's 5. Do we know the square root of 2? Nope. So we'll leave that as a square root of 2. So 5 square root of 2 is the simplified version of the square root of 50. Now let's look at the calculator here just to understand this. So what does this mean? Well, the square root of 50 is a number. Square root of 50, it's about 7.07. Okay? It's an irrational number. That's called an irrational number. Well, we said that's the same as 5 times the square root of 2. So if we go 5 times the square root of 2, we get the same number. And by the way, you don't actually need that square root of 2. Okay, this is a scientific calculator, by the way. This is desmos.com scientific. So the moral of the story is this: 5 times the square root of 2 is worth the same amount as the square root of 50. But this is approximate. Notice it stops here. It actually goes on forever and it never ends, it never repeats. This is an approximate number, 7.07106, so on and so forth. Exact, the square root of 50 is an exact number. 5 square root of 2 is an exact number. All right, we want to find exact values, but we want to write them in simplest form. 5 square root of 2 is, we've square rooted part of it, but not the other part. So simplifying just means we're finding another way to write it in a little simpler form. Okay, square root of 80. What can we multiply into the square root of 80? Well, 4 can go into the square root of 80. Oh, let's try that. That's probably the first one we jump onto there. Okay, so we can write this as 4 times 20. That's nice. So we can break that up into square root of 4 times the square root of 20. And we know the square root of 4. The square root of 4 is 2. And we don't know the square root of 20. I know the square root of 16 and 25, but not the square root of 20. Now, there it looks like we simplified it, but here's the thing. We didn't simplify it far enough. Now, we got 2 ways to go. We can either go back to the drawing board and start over and look for a bigger square root, which would be the best way to go, or we can take the long way. Now, I'm going to go ahead and take the long way first, and then I'll go back and show you what we probably should have done the first time. Now, we're going to keep this, so we have 2, but we're going to break up the square root of 20. The square root of 20 has another 4 in it, right? 4 goes in there again. So we can break this into 4, and I'm going to go ahead and, let's go ahead and just break this into 2 square roots here. So we have the square root of 4 times the square root of 5, and this is all multiplied here. And so this is just 2 times 2. 2 times 2 times the square root of 5, which is 4 square root of 5. That's our final answer, 4 square root of 5. Now, we did it in 2 steps, and we'd rather not do it in 2 steps, but it happens sometimes. So if you do it once, and you need to do it again, go right ahead. It's not that big a deal, but we have a better way of doing it. So let's back up. Let's go back to the drawing board and say, is there a perfect square that goes into 80? 4 does, but keep going. Does 9? No. Does 16? Yes. All right, so if you check on the calculator or work through it, this is 16 times 5. Okay. Now, one way you can also notice that is once you notice that it's 4 times 20, you know, if you go the 4 times 20 route and you say, hey, wait a minute, there's another 4 hiding in 20, that's because 4 times 4 is 16. We should have chosen 16. See that? So that's your clue that 16 is the number you want to go with, the largest perfect square. So we're going to break this into 16 times the square root of 5, okay? And that's going to be 4 times the square root of 5, and we are done. All right? How about cube roots? Well, this also works for cube roots. Now, cube roots, we don't want to think about these. We now want to think about perfect cubes. What perfect cubes go into this? Well, perfect cubes are numbers like 1 to the third power is 1. 2 to the third power is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. Okay? And we ask ourselves, do any of these multiply into 32? Well, 8 does. And the more you practice with this, the more you'll be familiar with it. That'll come up a whole lot. The cube root of 8 is a number that we can do. And what do we multiply 8 by to get 32? Well, it's 8 times 4. Okay, notice, by the way, I skipped this step. You can kind of skip this step once you get going. We're taking this and we're breaking it into 2 square roots, or cube roots in this case. A cube root we can do and a cube root we cannot do. I know the cube root of 8. The cube root of 8 is 2. We don't know the cube root of 4. So we write this as 2 times the cube root of 4. Okay? Now we got fifth roots. Oh boy. Well, once we get large exponents and a little more involved expression under here, you may want to use the second method that we talked about a few minutes ago. The second method is the prime factorization. And to do that, let's go ahead and just start breaking this up. This is 2 times 16. 16 is 2 times 8. 8 is 2 times 4. And 4 is 2 times 2. Now we have 2 times 2 times 2 times 2 times 2. Notice that's 5 2's. So we can rewrite this as 32 is 2 to the 5th, x, y to the 5th. Okay, just copy that last part down. Now, how do we simplify this? Well, now we're going to kind of go back to something that we started doing in the last lesson there, is we're going to break this up into 2 to the 5th, and let's take the y to the 5th. And we still have the x. It needs to be under its own square root. The x, the 5th root of x, we can't do anything with because there's no exponent here. This cannot be simplified, but these can. All right, so these can, and so technically, now here's a step you can probably skip, but I'll write it out. What we're really doing is that 5, that could be rewritten like that. Okay? And so what happens is this 5th root is going to cancel that. Again, probably could have skipped this step. This 5 is just going to cancel out both those 5's, both of them, because of what we just wrote. So this is going to be 2y. Okay? Now, what you'll see if you watch the other example videos from other people there, it's just if we have 5 2's, one of them comes out. If we have 5 y's, one of them comes out. Well, the reason is because there's an inverse operation, and that's important to understand. All right, so that's how you use that radical product rule to simplify when we have numbers and when we have numbers and variables. So we've seen how the radical product rule works really nice for simplifying radicals. It takes a number and we can break it into 2 square roots, part that we can square root, part that we can't, and we can simplify it. Now let's see how this works with variables. Okay, so remember that variables just represent numbers. So everything that we just did with those numbers also works here. Now, one other thing that we should notice here is that when we take the 5th root of 2 to the 5th, well, that power gets divided. It's a 5 divided by 5 becomes 2 to the 1st. Y to the 5th becomes y to the 1st. We don't usually put the 1st here, but that's the idea. It's y to the 1st, all right? So keep that in mind. That division is going to be important. All right, so what's going on here? Well, we want to break this up in the same kind of way. We're going to break it up into things we can square root and things we can't. And then looking ahead, our goal is going to be to take this and break it up into something squared. All right? And then the stuff that we can't deal with, we'll just leave under the square root. All right? So when we have 5 x's, or x to the 5th, well, if we write this as, if we break this up into x to the 4th and x to the 1st, then this number can be written as x squared squared. Okay, x squared squared is x to the 4th. So we can simplify an even number of x's, x to the 4th, an even power. All right, because that can be written as x squared squared. And what about y to the 6th? Can we simplify y to the 6th? I think we can, because y to the 6th can be written as y to the 3rd squared. Remember, when we have power to a power to a power multiplies. So y cubed to the 2nd power is y to the 6th. These are the same thing. Okay? So we can simplify y to the 6th. We can simplify x to the 4th. Now, I have to have 5 x's in my whole expression here, so I'm going to have 1 x left over in the cannot be simplified. So I like to think of this as, this is the things we can simplify, these are the things we cannot. Okay? Just like we did with the numbers a little bit ago. So, all right, we've broken up the y's, we've broken up the x's. Now let's break up the z's. Okay. So the z's, well, we want to figure out how many z's we can simplify so that we have 13. We have 13 z's all multiplied together. Well, we can simplify z squared. We can actually simplify up the most we can simplify is z to the 12th. So I'm going to break this up as z to the 12th, and then I got to have one more z here because z to the 12th times z to the 1st is z to the 13th. Okay, why do we pick 12? Well, one, because it's close as we can get to 13. That's an even number. All right, and so I can write that as z to the 6th squared. 6 times 2 is 12. Okay, and I've got this leftover z to the 1st I've got to leave in here. All right, so what's happening here? First of all, we're breaking this up into things we can simplify and things we can't. The things we can here, all these exponents are divisible by 2. 2 is the invisible index here, right? Because it's a square root. And this is a step that we'll probably skip this step eventually here once you really get it down. But the idea is we can write this as x squared squared, which is x to the 4th. Y to the 3rd squared, which is y to the 6th. Z to the 6th squared, which is z to the 12th. Okay? And in the end, these cancel. So this square cancels with that. Okay? And so we have x squared, y cubed, z to the 6th times the square root of x, z. Okay? So basically we took out every pair. And another way you could do this is we could write this all out. And if you watch other videos, you'll see this written out: x, 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 y, 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 y. You'll see people write them all out. And it's a whole bunch of extra writing that we don't need, okay? Every pair of x's is going to be simplified because we can break it up into these terms squared, or these factors squared, all right? And so that's the idea. Now let's try one more. What about cube rooting? All right, well, when we're cube rooting, so we want to break this into things we can cube root and things we can't. All right, so first we look at the number. Can we cube root 54? Well, no, we can't. Now, the simplest way to do this is to think about your perfect cubes. Our cubes are 1 times 1 times 1. 1 to the 3rd power is 1. 2 to the 3rd power is 8. 2 times 2 times 2. 3 times 3 times 3 is 27. And 4 to the 3rd power is 64. And that's enough. Do any of these multiply into 54? Does 8 go into 54? No, it does not. Does 27? I think it does. 27 times 2 is 54. So we can cube root 27. That's something we can cube root, but we can't cube root 2. 27 times 2 is 54. Can we take the cube root of x to the 3rd? We sure can. Cube root of x to the 3rd is just x, and we'll do that in a second. So we only have 3 x's here. We don't need any in the leftovers because all of our x's are in the can cube root. Okay, what about the y to the 8th? Well, 8 is not divisible by 3, so we cannot cube root that. Okay, so what's the closest multiple of 3 that we can get that's close to 8? Well, that is y to the 6th. But we need to have, we have 8 y's, y to the 8th, and so we need 2 of them over here. All of this has to be equal to this. We have to have all the ingredients. We're just splitting the ingredients up here, all right? And then we have z to the 22. Is 22 divisible by 3? Nope. The closest we can get is 21. So we have z to the 21. But we need to have 22 z's, so I need to have 1 extra z over there. 21 plus 1 is 22. All right. So what does that do for us? Well, we have our leftovers here that we can't deal with. 2y squared z to the 1st. Let's try that a little better. There it is. Okay. And then We can, this we can write as the cube root. And we want to write this out. I'm going to go ahead and write this out as something cubed. So we want to think 27 is 3 cubed. X to the third is x cubed. All right, so notice this little cubed. It's kind of hard to read over there. Let me make it a little nicer. Okay, we've got cubed. Okay, so under this radical, we have x cubed, 3 cubed. What do you have to cube to get y to the 6? Well, it's y squared, because 2 times 3 is 6. Power to a power gives us 6. What do we have to cube to get 21? Well, we have to cube, we got z to the 7th. 7 times 3 is 21. Okay? All right, and so all of these cancel. All that we're doing, all that's going on is we're dividing each of these by 3. Okay, so we're pulling out as many, the biggest multiple of 3 we can. Those all getting divided by 3. We got a 1, 2, and a 7. And that leaves us with our final answer of the cube root, nope, sorry, I just did the cube root of 3x to the first, y to the second, z to the 7th, times the cube root of the extras 2y squared z to the first. You don't have to put the first on the z. All right, so that's the idea. Okay, notice all that really happened was we took as many 3's out as we could, x to the third, and it got cube rooted, became an x. We took as many 3's out of here. Okay, there's 6. 2 times 3, there's 2 3's, and the remainder is 2. There's 7 3's and 22, and we're left over with 1. Okay, so this is the ones we can't simplify, and this is. Okay, now I got to back up. We forgot one little thing here. Notice in the instructions, okay, we've got to use absolute value signs. In other words, we've got to ask ourselves, can these be negative? Is it okay for cube root to be a negative number? Yes, it is. Odd roots can be negative. We do not need absolute values there. But let's back up here. This has to be positive. So we have to ask ourselves, can these be negative? Yes, this one can. Okay, x squared, well, no matter what number x is, this will be positive because an even power will be positive. But y to the third power, this could be negative because a third power, if you put a negative number in there, that could be negative. So we should have a negative, we should have absolute values there to keep that positive. Okay, you might write this like this: x squared z to the 6th, absolute value of y cubed, and then the square root of xz. So the idea is anything that comes out, we've got to make sure that that's positive if we took the square root, because this is an even root. Okay, and a little reminder, even roots that lead to odd powers need absolute value. Okay, even roots, this is a square root. This is an even number. 3 is not an even number, but 2, that is an even number. Okay, even roots that lead to an odd power need absolute values. Okay, don't get too hung up on that. It's important. It's not too major. Okay, the idea is we just need to make sure this is positive. All right. So that's simplifying with the radical product rule. Next, we're going to move on to the dividing radical expressions. So dividing radical expressions actually works the same way, or very similar, I should say, as multiplying, all right, with a few little twists. So if we take the cube root of 27/8, well, we can just cube root that fraction, ask ourselves, what number, or what is the cube root of 27, and what is the cube root of 8? Well, the cube root of 27 is 3, and the cube root of 8 is 2. And we can double check, 3 halves times 3 halves times 3 halves. 3 times 3 times 3 on top is 27. 2 times 2 times 2 on bottom is 8. So the moral of the story is, if we're cube rooting a a fraction, we can just cube it at the top and cube it at the bottom. And this works both ways. So this is the radical quotient rule. If you're taking a root of a quotient, right, or a fraction, because a fraction is a quotient, a fraction is a division problem, then we can take the nth root of the top and the nth root of the bottom. All right, and that's the key. So let's try some examples. So here we want to simplify these roots, these radicals here. All right, so we're going to cube root the top, cube root 16. Oh, let's back up here. We got one practical thing we got to ask ourselves first, okay, before we go too far. First, ask yourself, can you simplify 16 27ths? Is there any number that goes into 16 and 27? Well, the answer is no. There is no common factor for 16 or 27. So we are just going to simplify those. Well, we know the cube root of 27, that is 3. Now we don't know the cube root of 16, so we got to break this up. And this is what we did with the radical product rule. We look for something that a perfect cube that is in 16 times some leftover number. All right, and so we ask ourselves, what perfect cube goes into 16? Well, 8 is a perfect cube. 8 is 2 to the third power. So 8 times 2 is 16. We break into things we can cube root and things we can't. Okay, remember, simplify means we want an exact answer, no decimals here. The cube root of 8 is 2. And then we have the cube root of 2 left over and 3 on the bottom. That is our simplified version of the cube root of 16 27ths. Okay. How about 24 1/25ths? Again, ask yourself, can you divide these? Okay. Now you might want to pause this and try this. It's very similar to the last one. Why don't you pause this? See if you can do that, and then come back to the video for a second. All right. The idea is we break it up. Cube root of 24. Cube root of 125. Do we know the cube root of 25? 125? We do. It's 5. Is 24 a perfect cube? No. 27 is. 27 is 3 to the third power, but 24 is not. So we got to break this up into 2 radicals. What is the perfect cube that goes into 24? Our perfect cubes are 1, 8, 27. Does 8 multiply into there? Yes, it does. It's 8 times 3. We can simplify the cube root of 8. The cube root of 8 is 2. The cube root of 3, we don't know. It's a decimal number. And 5 stays the same. Okay? If you can simplify these, then go ahead and do that, but you can't. All right. Again, you need to ask yourself, can you simplify these first? All right. And that'll show up. And let me do one more example here. Let me say B.2 maybe. Okay, example. Let's say we had the cube root of, let's say we had 16 over 54. Well, is there a common factor in 16 and 24 or 54? There is. It's 2. We can divide top and bottom by 2. So if we divide by 2, just simplifying the fraction, we get 8 over 27. Okay? So always look for that first. And the cube root of 8 over the cube root of 27, that would be 2/3. Okay? All right, always look for that first. So, all right, we can throw some variables into the mix here. Square root of 9x cubed over the square root of y to the 10th. There's nothing that can cancel here. Look at that ahead of time. Do we know the square root of y to the 10th? Okay, well, we do. So this is, we can write this as the square root of y to the 5th squared. And once you get a good grip on this, this is a step you can skip. It's going to be y to the 5th. These are just going to cancel. 5 times 2 is 10. So this is going to simplify to y to the 5th. Can we simplify this? Nope. but we can simplify part of it. Do you know the square root of 9? We sure do. Do we know the square root of x to the third? No, but we can break it up into x squared, which we can take the square root of x, and x to the first. Okay, so that leaves us with, on bottom, y to the fifth. On top, the square root of 9 is 3, and the square root of x squared is x. And then we have this leftover square root of x that's just kind of hanging out. We can't do anything with it because the exponent is 1. Okay? Again, notice, when we're simplifying y to the 10th, it just gets cut in half because the index is 2. Okay? All right? You might pause it and try this one. Very similar. First, ask yourself, can you cancel anything here? No, you can't. So we break it into 2 cube roots, 8y to the 7th, and the cube root of x cubed. We know the cube root of x cubed is just x. The cube root here, we got to break this into 2 cube roots, what we can cube root and what we can't. Can we cube root 8? Sure can. Can we take the cube root of y to the 7th? No, because that's not divisible by 3. What is the closest exponent that is? The closest we can get is y to the 6th. We've got to have 7y, so we need to have 1y in the I can't handle it radical. So this is the radical we can cube root. This is the radical we can't do anything with. 6 plus 1 is 7. Still have our 7y's using the radical product rule. All right? And so let's go ahead and clean up that top stuff. Cube root of 8 there is 2. And the cube root of y to the 6th, that's going to be y squared. And then we have the cube root of y to the first left over. There it is. Okay? All right. So that's how we simplify with division. Let's look at a couple more situations here where they're already broken up and we want to simplify this. Well, the key here is we want to combine them first. So if they're separated, combine them first, then simplify before you dive into it, all right? So we'll see that helps a lot. If you just start square rooting here, it's going to get ugly. So first put them together, 40x to the 5th over 2x. We know what 40 divided by 2 is. 40 divided by 2 is 20. And x to the 5th divided by x to the first. Do you remember the rule there? We're going to subtract those exponents because x to the 5th, a little side note here, over x to the first, that is x times x times x times x times x all over x to the first. And if you take these two x's here, x divided by x is 1. So this is really 1 times x times x times x times x. In other words, x to the 4th. Well, we don't want to write this out every time. When we're dividing powers, we subtract the exponents. 5 minus 1 is 4. So this simplifies to x to the 4th. These two divide. Well, look, we don't even have a fraction anymore. So let's go ahead and break it up. Things we can square root and things we can't square root. Okay, 20. We can't simplify the square root of 20, but there's a 4 in there. 4 is a perfect square. We look for a perfect square in 20. It's 4 times 5. 4 times 5, okay, is 20. And x to the 4th, well, that is an even power, so we can simplify that, okay? Here's the step that we can skip once we get this down, okay? 2 squared is 4, and x squared is x to the 4th. X squared squared is x to the 4th. 2 to the 2nd power is 4, okay? And then we've got the square root of 5 hanging out. So that square root cancels with the squared, and we're left with what's in the parentheses. In other words, we square root the 4 and we get 2. We square root the x to the 4th and we get x squared. There it is. Okay. Do we need absolute values? It's squared. Okay, it's an even index. Do we end up with an odd power? No, so we don't need absolute values. You never need absolute values around numbers, just variables. Okay, one more here. Put them together. 48x to the 8th y over 6xy to the 4th. Okay, now subtract. Okay, so if we have 48 divided, we'll subtract exponents here. Divide 48 divided by 6, that is 8. 6 times 8 is 48. Okay, x to the 8th divided by x to the 1st will be x to the 7th. Now the y's, there's more y's on the bottom. So one y will cancel with 1. So this one will cancel with one of those, leaving us with 3 y's, but those 3 y's are on the bottom. All right, so we got to leave them on the bottom there. There's more y's on the bottom, so the leftovers will be there. Okay, that leaves us with this. Now we can break it up into 2 radicals. Cube root of 8y to the 7th on top, and then cube root of y to the 3rd on the bottom. We get y on the bottom, and we got to break up the top. Can we cube root 8? Yep. We can cube root y to the 6th, because that's a multiple of 3. And we got 1y we can't. So 6 plus 1 is 7. Why did we choose 6? Because it's a multiple of 3. Okay. And then we've got this y on the bottom. We've got this cube root of y up top. The cube root of 8 is 2. The cube root of y to the 6th is y squared. Okay? All right. So that's how we simplify with dividing. Put it together first, divide and clean it up, simplify the fraction, and then work it out.